All right, let's talk about something that sounds completely impossible. We're going to dive into a wild phenomenon where solid ground, the very stuff you walk on, can suddenly start behaving like a liquid. No, it's not science fiction. It's a very real engineering problem called sand boiling. I mean, think about it. The ground beneath our feet is supposed to be the definition of solid, right? Stable. But under the right conditions, that all goes out the window. So how on earth can that happen? How can dirt turn into a fluid?
So first things first, let's really nail down what we're talking about here. What does it actually mean when solid ground starts to flow?
Okay, the key here is to forget about heat. The term boiling is a little misleading. This has nothing to do with temperature. It's all about water pressure. Imagine water flowing up through the soil with so much force that it literally lifts the sand particles. Suddenly, they're not packed together anymore. They're just floating. And when that happens, the soil loses all of its strength and starts to churn, just like a thick, bubbling liquid.
So we know what it is, but the big question is why? To get that, we need to look at the invisible forces that are constantly at play, deep under the surface. You can think of it like a constant battle, a tug of war happening inside the soil. In one corner, you have effective stress. That's just the downward force of the soil particles themselves, holding everything together, keeping it solid. But in the other corner, you have upward seepage pressure. That's water pushing its way up from below, trying to pry all those particles apart. Now, most of the time, effective stress wins, no problem, but that balance can shift. And when it does, it's like a chain reaction. First, that upward water pressure just gets too strong. It overcomes the weight of the sand and starts to lift those individual particles. As soon as those particles are suspended in the water, the whole structure of the soil is gone. Poof! Its strength completely vanishes. And the results? It starts behaving just like a liquid, totally unable to support any weight. Now, this isn't some random accident. It's actually very predictable. There is a precise, calculable moment when that solid ground will fail. And, you guessed it, engineers have a formula for it.
So what is that breaking point? When does the soil finally lose the fight? Well, the answer is all about something called the critical hydraulic gradient. That sounds complicated, but just think of it as a way to measure how hard that water is pushing upwards. Once that push gets too strong, once the gradient gets too steep, the soil fails.
Now, the formula that tells us this tipping point has two main parts. The first one is G, which stands for specific gravity. Don't let the name fool you, it's a simple idea. It's just a measure of how dense the solid soil particles are compared to water. It's a basic property of whatever sand or silt you're working with. And the second piece of the puzzle is E, the void ratio. This is just a fancy term for the amount of empty space between all those soil particles. You know, loose, fluffy sand has a lot of empty space, a high void ratio. Densely packed sand has a low one. And these little empty spaces are super important because that's where the water flows and builds up all that pressure. And here it is. This is the formula that can predict a disaster. That I see on the left, that's our critical hydraulic gradient, the magic number. Now, for most common sands out there, this whole equation works out to be a number right around 1. So when the actual pressure from the upward flowing water hits that value, that's it. Game over. That is the mathematical line separating solid from liquid. Okay, so theory and math are great, but where does this become a real-world life-or-death problem that engineers have to deal with every single day?
Well, you see it in a lot of common construction scenarios. Anytime you have to dig a deep foundation for a building and you go below the water table, you've just created the perfect recipe for sand boiling. It's also a huge risk for things like cofferdams. You know, those temporary walls they build in rivers to create a dry workspace? Water is always trying to seep up from underneath them.
So knowing the danger is one thing, but preventing it, that's what engineering is all about. How do we fight back against these forces and make sure the ground stays solid? Thankfully, engineers have a whole toolkit to stop this from happening. The most direct method? Just pump the water out of the ground. If you lower the water table, you directly reduce that upward pressure. Simple. They can also install special filters that let water pass through but trap the soil particles, or even design longer paths for the water to travel, which makes it lose its energy. It's all about managing that underground battle of forces. So if you take one thing away from all of this, let it be this. Sand boiling is a failure caused by seepage. That means water flowing through the soil. It is not a shear failure, which is when soil slides sideways. That distinction might sound small, but for an engineer, it's everything. It changes exactly how you design a structure to be safe and stable. And that really brings us to a final thought. Sand boiling is just such a powerful reminder of the incredible and usually invisible forces that are at work right under our feet all the time. It really makes you wonder, what other hidden forces are out there, constantly shaping the very ground that we build our entire world on?